Today, I will talk about how to build performance services with the new features of .NET 7.0 that ship today. So what we'll talk about is protocol improvements like HTTP2 and HTTP3 improvements in terms of performance and also some new features. We'll talk about rate limiting, which is new in .NET 7 and also new in .NET 7 output caching. And all of these should make your apps much faster. I hope so. Some reminder that this session might contain some monsters. So if you're afraid of monsters, please be careful or skip the part with monsters. Let's start with HTTP2 improvements. First with performance. So some new features in HTTP2 in .NET 7.0 for Kestrel. Main change in HTTP2 was from a refactoring of how it works internally to be using channels, which is an asynchronous concurrent queue that is used now to maintain streams over HTTP2. So there's a link in the pull request here, but if we take two different benchmarks here, the first one went from 110,000 RPS to 4 million RPS. And the second benchmark went from 1.2 million to 6.8 million, just because of this change on HTTP2. So I really urge you to switch to .NET 7 if you are using HTTP2, for instance, for gRPC. Another perf improvement that was made in .NET 7 for HTTP2 is how the data frame size negotiation has been updated to allow for faster throughput when the network has a high latency. So that's also very important. And like your uploads could go like from 40 seconds to 5 seconds because of this change. Another change on HTTP2 is the support for WebSockets. WebSockets is a bidirectional communication mechanism in HTTP. And by default on HTTP1, you can only have one stream of data per connection, which means per endpoint, actually. With HTTP2 and the new support in Kestrel for WebSockets, you can have multiple endpoints shared across the same connection. However, you might still be, each stream might still impact the other one. So that we'll see other improvements later. And there is no configuration required. So let's jump into a quick demo just to warm up the fingers and the brains. So here I have a sample web app that will create a WebSocket with a client. And it's very simple code. So the standard minimal API code with a hello world endpoint, and then a WS endpoint that will create the WebSocket, that will connect to WebSocket request. And when it's connected, it will just wait for messages to come and then send an echo message with the same payload. And this is what this is doing, is just receiving a message and then sending the same thing and waiting for the next message until the next message is to close the connection. So let's see if I can just change this code and add some message when we receive some WebSocket communication. So I save it, and here I should have the application running here. So this is my application running. And if I go on this site here, I will open this URL. And I can see here that I have a communication with this page, with the hello world page on HTTP2. If I go on this WebSocket client and I start to connect to the same service but on the WS endpoint, I will connect. And you can see that this connection has been made with HTTP2 Connect, which means we are talking with a WebSocket on HTTP2. Also important to note that I didn't change the default protocols that are listened to in Kestrel because the default in .NET 7 are HTTP1 and HTTP2. So that's how it upgraded automatically to HTTP2 when I connected with the homepage, and how the WebSocket used HTTP2 because I already had a connection from the browser with HTTP2. Going back to the slides and talking about HTTP3. So HTTP3, for those who don't know, is a newish protocol that uses QUIC, which is based on UDP instead of TCP. And what it means is that the traffic is supposed to be faster, less latency. It's supported by Chrome, Edge, Firefox, Opera, and Safari, but in optional mode. So you have to opt in Safari to be able to use that. In Kestrel, it was experimental in .NET 6 when it was introduced. And in .NET 7, it's now no more experimental, but it's still enabled only by configuration. Some improvements in .NET 7 also were made on HTTP 3 since last year. It was first released. On reliability, on the API shape, so some changes. That's why it was experimental, so we could play with how to use the HTTP 3 protocol. On the correctness, so it's just work better compared to the specification, and also performance improvements on HTTP 3. This is how you would opt in into the HTTP 3 protocol from an ASP.NET Core app. So by default, I just said a minute ago that HTTP 1 and HTTP 2 are supported when you don't say anything, but you can change that to force any specific protocol and also to support HTTP 3 automatically. In terms of performance, some changes for HTTP 3 are memory allocations improvements. And whenever you allocate less, your app will go faster in terms of RPS, in terms of latency, because less garbage collections. So that's a very important point in .NET 7 for HTTP 3. Another improvement is how the headers encoding is done, which is one of the main features of HTTP 3. So lots of improvements on the QPAC algorithm implementation in .NET. And finally, a new feature in HTTP 3 in .NET 7, for HTTP 3 in .NET 7, is WebTransport. So I talked about it earlier. WebSockets in HTTP 1 requires a connection per stream. So if you have a stream of data back and forth from the client and the server, you have one connection. And if you need 2 streams of data, then you need 2 connections. And so it doesn't scale much. With HTTP 2 and the WebSocket support, it scales better because on a single connection, we can multiplex multiple streams of data. And that solves an issue. However, because how it's done with TCP, if you lose a packet, then on a stream, other streams of data will be impacted in terms of performance. So that's not the best way to get the communication working. With HTTP 3, on a single connection, you have independent streams. So even if one stream gets slowed down, the other streams won't get impacted. This feature, WebTransport, is the way it's supported. It's not WebSockets, it's a new kind of transport. And in .NET 7, it's experimental because it's still a draft, actually. I linked here to a document that explains how to use it in .NET 7. We won't have time to show that today. Now, let's talk about rate limiting. So rate limiting is a new feature in .NET 7. And the idea of rate limiting is to be able to limit how many requests you will receive on your web app. One reason might be to protect the overall health of your system. Imagine that you have a request that goes to the database, and the database queries might be slow and you can't support lots of them at the same time. If you accept too many requests from your clients, you might get the database to go down because it's using too much resources. So one way of fixing that is to limit the rate of the requests that come in. You might also think about it to be able to provide an SLA to your application. Like if your application says that you have to answer to any request in less than 10 milliseconds, you can't accept all the requests that maybe your clients would like to send. So by limiting this number of requests, you might be able to support the SLA you're setting. Another way to use rate limiting is to prevent abuse from some users. Some users might just send a burst of data to test your system to see if they can take it down, like denial of service. And by using rate limit, you can define how many requests you can set per user, for instance, to define these API usage limits. So defining per user or based on the subscription level, because you might want any user, any standard user, any anonymous user to be limited to a specific number of requests per second. But maybe you want your subscribers, your actual customers, to have more than this. And it's also a way to enforce or to encourage customers to go to a subscription level. Example is GitHub. I assume most of you are familiar with GitHub, and that's what GitHub does. By default, when you go to an API on GitHub, as an anonymous user, you will be limited to 60 requests per hour. Okay? And once you reach these 60 requests in 1 hour, then you will get some kind of error message. A nice message telling you you've reached your rate limit, so you need to wait for the next hour, or to authenticate, because on GitHub, when you're an authenticated user, then you get 5,000 requests per hour. So that's a very good example on how you could implement rate limiting in .NET 7 in ASP.NET Core. So what are the features that rate limiting provide? Simply speaking, rate limiting is defining a number of leases that are issued, and each request that comes in is taking a lease. So the idea is to have as many requests as leases you have. And if you have more requests, then you have not enough leases available, so you will get an error message. There are many ways to issue leases from rate limiting features. The first way is to use a fixed time window. What it means is that, let's say, for the next hour, I will grant 60 leases. And once these 60 leases have been taken by a request, then you will have to wait for the next hour window to get a new set of 60 leases to be available for your request. That's the simplest way to implement rate limiting. Another way is to use a sliding time window. It's like the fixed time window, but assume that this hour, this time frame of an hour, will move along with the time. So if you send a burst of 60 requests in the first hour at the beginning of the hour, you might not have to wait for the next full hour to get renewed the 60. Or if you just send 10 at the beginning of the hour, these 10 will come back after a specific amount of time, not the full hour. So the window of time is sliding continuously. Then there is the concurrency limit, which lets you define how many concurrent requests at the same time can be alive on the server. That's a good limit to define as a global limit if you want to prevent whatever the amount of API rate limit you have for each user. You might want to have a global limit to say, well, whatever's happening, I don't want more than 10 users on my machine because I know the database cannot support that. That's an example. And in this case, it's not the number of leads, but not the number of concurrent leads at the same time. A token bucket limit is behaving in a way that the leases are replenished every period of time, and at the same time, so what's happening is that it's not a sliding window, like it's not replenished based on the usage, but it's just adding more and more leads every period of time. Let's say if the period of time is 1 minute and I want to replenish 2 leases, every 1 minute you will get 2 more leads added to your bucket. And if your bucket is full, that's fine. But every time you take a lead from the bucket is emptying itself. So the idea is that there is a stream of leads coming into your bucket that you define, and then your request will take some out of this bucket. Finally, a feature of rate limiting is partitioning. That lets you define all of these limits per custom values. This custom value could be a user, an IP address, a company, whatever you want, a subscription ID. It's up to you to define whatever value you want. So this will allow you to define those limits in a fair way for all your users. So you can define what is the partition you want to assign to all your limits. Let's jump into a demo for rate limiting. So if I open this one here I have an empty application, default empty applications, and well, what it's doing is that when I run this application, it will write a gravatar. So let's open this thing. This is my application, and when I refresh here, you can see I get a new monster every time. This monster is randomly generated, and what we get is the counter of monster generated, the time it was generated, and the connection identifier. So here the last two letters are important, D9. And if I refresh, I have the same connection. I'm generating a new monster. You can see at the same time, on the bottom right, that the same information is rendered in the output of my application on my window here. You see the same thing, the same connection is used. And what I will use also is a load generator named Bombardier that will create lots of connections, lots of requests. Here I will say one connection, and I will tell Bombardier to generate 10 requests as fast as it can on this single connection. So if I hit enter, you will see here that I got 10 requests, 10 responses with 200 results, so they all worked. And in my log, I saw all these ones appearing. So now let's add rate limiting, because I don't want my users to be able to send requests that fast. Going back here, we'll first add the add rate limiter options and services. And I will just grab this example. Oops, I typed too much. So here what I have is add rate limiter to add the service and options, and add fixed window limiter that will create a fixed window limiter named not so fast, with an option of a window of 1 second and 3 permit limit, 3 leases. So every second I will get the 3 requests available, and the next second I will get 3 more. If I use my 3 requests, then I can't do anything more. So if I run that, and I go to generate monsters by refreshing, I get all my monsters. But if I go faster, like, oh, sorry, it doesn't work because I need to enable the service. So app.use rate limiter. And I also need to protect my endpoint by saying require limiter with the not so fast policy that we just created. Starting it again. And now if I refresh, I'm getting 1, 2, 3, 4, some 503 answers. If I started from Bombardier, which will send 10 requests as fast as it can, I'm also getting 3 good responses and 7 bad responses, which are rejected. Now, let's fix that and say, I don't want my users to be blocked by this. I want them to wait for the next available window instead of being rejected as soon as we can. So here I will say queue limit and say 1. What's happening then is, as I send my 10 requests as fast as I can, there is some delay, it's slower, but they will all come through. They will all be served. And what I see here is they are all using the same connection, AL, but the first request comes on the second 44, and then the third one on the second 45th, which is exactly 1 second after the first one, because it was this third one was waiting for list to be available. And as soon as it was there, I get my 2 other requests in the same second, and then 3 in the next second, and then again in the next second. So this way, we are limiting the rate, but we are not preventing our clients from being served a response. Now, imagine I create 2 connections. And I run the 10 requests as fast as I can, but I need to unblock this app. This time, they are not served. I get 6 requests served and 4 which were not served. What's happening is that the first 3 requests got through, then we were queued, and then some seconds passed, and then I got a new list, but some of them didn't get through. So what we can do in this case is partition our rate limit to support different connections. So to do that, I will use a little more a rate limit which is a little bit different to be configured, but that allows me to define here a custom partition. And to partition my rate limit, I will use the identifier of the connection. So each connection will get the same rate limit, which is 3 leads per second with a queue limit of 1. So if I save that, and I send my same load with, oh, this one should restart. Which is here. So if I start it again, this time, because I have a partition per ID, per connection ID, I have all my requests that have been served. Okay? So that's how you configure the partitioning. And this partitioning can be further enhanced by, for instance, setting different limits per user if the user is authenticated, or per remote IP address if the user is anonymous. So you can say that each different connection, each different company will get a different set of leases. So that's how you do rate limiting in .NET 7. So now output caching, which is also a new feature in .NET 7, will allow you to not process the same server request if it renders the same value. So this way we'll store the result and reuse it across the next request. In .NET 7, you can store it in memory by default, but also on disk, on Redis, and blob storage. It will also prevent cache stampede and thundering herd, which will happen if your site starts up and then all your clients come at the same time and want to get the same result. And it can invalidate cache entries by tag if you need to be able to invalidate a full section of your site. And finally, it supports cache revalidation, which is a way of returning a not modified answer if the value you have in the client is the same as the server will return if it was cached. So let's see a small demo of that. I will remove this policy that we don't need. I will remove the queue limit. And I will add output caching. Here I'm defining a pretty fast policy that will expire after 3 seconds. I need to use the output caching, and I need to add output cache on this endpoint. And what's happening here, if I send the same load, is that I can see there is a single request, but it's still rate limited. A single request is good because it was cached, but still rate limited because I use the output cache after the rate limiting. If I use it before the rate limiting, then all my requests are answered and a single monster has been generated on the server side. Something you might not see here, if I use latencies, we'll see that. If I disabled a default feature which is called locking that prevents cache stampede, we will see, and we will see, I need to remove the 2 connections because I need lots of connections to send the traffic as fast as we can. And I can't see that. Let's see. Did I save? It doesn't work. So I don't know what. We should have seen that by disabling the set locking, we need to see a burst of requests because they are not cached. Or maybe my monster are generated too fast and I can't trigger that. That's OK. You'll trust me. It should have worked. But here we see that's weird because set locking is false, and I can see they all serve at the same time. That's worrying. Too bad. So we should have seen that without locking, all the requests are processed by a server. And with locking, which is a default, only a single request has been processed and all the other ones got the same result. As a conclusion, so you get, by upgrading to .NET 7, you get free performance, which means just upgrade it and you get free performance. Nothing to do on your web app. And then there are some features that will give you marginal gains, but when you add up all these marginal gains, you get much better performance. And we saw WebSockets improvements, WebTransport, new rate limiting features, and finally the new output caching feature to improve your applications. Thanks everyone.